All right, let's get into one of the most foundational and honestly coolest ideas in all of computer science, the tree. It's a concept that quietly organizes our entire digital world in ways you probably don't even realize. I mean, really think about that for a second. You hit search and boom, almost instantly your machine finds that one specific file out of a complete sea of data. How in the world is that even possible? Well, it's not magic, it's just a really, really smart way of organizing things. You see, if your computer just kept one long, single list of every file you have, it would have to check them one by one. That would be unbelievably slow, a total nightmare. Instead, it uses a branching hierarchical method, what we call a tree, and that lets it slash through the possibilities exponentially faster. So let's unpack that. How do we get from that slow, simple list to this incredibly efficient hierarchy? Well, this is exactly where the idea of the tree comes into play. At its heart, a tree is just a way to store stuff that has a natural parent-child relationship. You know, a family tree is the perfect real-world example. But the file system on your computer, that's the perfect digital one. You've got a main drive, right? That's the ancestor. And inside it are folders, and those folders have more folders and files inside them. It's a hierarchy. That's all it is, really. So let's stick with that file system idea. The single main drive, like your C drive, that's what we call the root. It's the beginning of everything. Any folder inside of it is a child, which makes the drive its parent. Simple enough, right? And what about a file itself, like a photo or a document? Since it can't have anything inside it, we call it a leaf. See? Every part of the hierarchy gets a name. Okay, now let's zoom in on a very specific and seriously powerful kind of tree. This is the one that makes searching so blazingly fast, the binary search tree, or BST for short. The whole magic trick of a binary search tree comes down to one simple but absolutely brilliant rule. For any given spot on the tree, anything that branches off to the left has a smaller value, and everything that branches to the right has a larger one. That's it. That one little rule turns a basic tree into a high-speed search engine. So how does that work in the real world? It's just a super simple, repeated process. You start at the very top, the root, and you ask one question. Is the thing I'm looking for bigger or smaller than where I am now? If it's smaller, you just ignore the entire right half of the tree and go left. If it's bigger, you ignore the left half and go right. You just keep doing that, and with every single step, you cut your search area in half. It's a classic divide and conquer strategy, and it is incredibly effective. But you knew there was a catch, right? The binary search tree has a kind of Achilles heel, a hidden flaw that can completely destroy its speed. Let's talk about the unbalanced tree problem. In a perfect world, our tree is balanced. You know, it's nice and bushy, symmetrical. This shape guarantees that every search is super short and direct. This is the goal, the ideal state where the tree is performing at its absolute best. But what happens if we add our data in order? Like we add the number 1, then 2, then 3, then 4. Well, the tree stops branching out. It just becomes this long, spindly, pathetic-looking chain. And what have we created? We're right back where we started, with a slow, simple list. All that search speed? Gone. And this right here shows you just how high the stakes are. For a nice, balanced tree with 10,000 items, finding something takes at most 14 checks. 14! But if that same tree becomes totally unbalanced, well, in the worst-case scenario, you could be looking at 10,000 checks. The performance difference is just staggering. So, what's the fix? How do we stop our beautiful, fast tree from turning into this slow, clunky list? Well, this is where computer scientists got really clever. So, say hello to the self-balancing tree. A great example is the AVL tree. It's basically a regular binary search tree, but with a built-in superpower. It's constantly watching its own shape. It has a rule that says the 2 branches below any point can never have a height difference of more than 1. Think about it like this. Every single time you add or remove an item, the tree does a little self-check. It looks up from where the change was made and asks, hey, did this change make anything lopsided? Is one side of me now way taller than the other? And when it does find an imbalance, it performs this elegant little fix called a rotation. It's kind of like adjusting one of those hanging mobile sculptures. It just takes a few nodes, the unbalanced one, its parent, and its child, and shuffles them around. The heavy side moves up, the old parent moves down, and the tree's compact shape is restored, all without breaking that left is less, right is greater rule. And just like that, balance is restored. The tree is short, bushy, and efficient all over again. This constant self-correction means the tree always gives us that lightning-fast performance we count on. Okay, so the binary search tree is an absolute master of searching. But what if your goal is different? What if you don't need to find any random item, but you need instant access to the single most important one, the biggest or the smallest? For that job, we need a totally different kind of tree. This is a heap. Now, unlike a BST, it's not strictly ordered from left to right. Instead, it follows an even simpler rule. In what's called a max heap, every parent is bigger than its children. That's it. And what that means is the biggest item in the entire collection is always, without fail, sitting right at the very top, at the root. And this really highlights why you'd use one over the other. A binary search tree is like a perfectly organized library index. It's designed to help you find any book really fast. A heap, on the other hand, is more like a king of the hill game. Its entire purpose is to make sure the champion, the biggest or smallest item, is always right there on top, ready to go. Think about an emergency room queue where the most critical patient has to be next. That's a perfect job for a heap. And this isn't just abstract theory, you know? These structures are the invisible backbone of the tech you use every single day. Your computer's file system, the database indexes that make websites load so fast, the compilers that turn code into programs, those priority queues managing tasks in your operating system. They all rely on the elegant logic of trees. So, once you start to see this beautiful logic of a tree, this constant quest for order in a chaotic sea of data, it really makes you wonder, doesn't it? What other simple, powerful ideas like this are quietly and efficiently running the world right under our fingertips?